Hello, in this video I would like to talk about integration. In particular, I want to talk about the integral as the area under a curve. What follows isn't so much of a rigorous proof, although in future videos I would be more than happy to offer a rigorous proof. I know quite a few, or I know a few, and a couple of them are actually really quite beautiful. Also, be great to do a more formal proof on integration on integration by parts in the future. But having said all that, in this video, this is part of a series, just a very short series that I suppose pays homage to, or just reflects on how I taught myself calculus. And in this video, we're just going to kind of look at a proof. You could call it a proof, maybe. One of the first that I discovered and that I had learned, and I would describe it more as intuitive reasoning, really. And so, like the videos on differentiation, let's start with considering just some basic line graphs, and then we'll sort of build up. That's really how I did it before I was more formally introduced to calculus. And so what we want to do is let's just start with this graph right here on the left hand side. Now this is just a basic velocity time graph that one should probably be quite familiar with, and we can see here that velocity is fixed at 50, right? We have here on the in the vertical axis, our v axis, we've got our value at 50 set right across. And so if someone were to ask us, well, what was the distance traveled, let's say, at 2 hours? So, I don't know, let's just draw a line up right here. Distance traveled. Well, one would know from spending likely many years working with line graphs that what we would want to do is find the area under this line up until the point x equals, well in this case, t equals 2, right? So, to find that area, we know it would just be 2 times 50, wouldn't it? So the distance traveled, and let's just say it's in miles, would be 100 miles at 2 hours. But what if one said, okay, well that's great, what is the distance traveled then at 4 hours? And so we've got our 4 here marked. I've already marked it in advance just to sort of save some time. And of course we would just basically undergo the same procedure. And so it'd be this entire shaded area under the line, right? And we would just say, okay, well it's the area, or the distance traveled would be 4 times 50, or in other words we could say the area under this line, let's just write it this way, the area under the line is 200, right? 4 times 50 is 200. So that's quite simple, it's simple enough, and we can analyze this graph a little bit more. Even the most simplest of graphs reveal lots of information, and we can say, oh well, we know the velocity is fixed at 50 miles per hour, and we know that the a, if a equals area, a also increases at a constant rate, or one could say in a linear fashion, with time. In other words, like if we were to extend this graph out, say to 6 hours, well the area is also going to increase, right, at a constant rate with that increase in time. So it's just a very simple principle. Now on the right hand side we've got another line graph here. This is different. This is a distance time graph, and actually maybe perhaps I should have made it a velocity time graph, in which case we would know. And if one is already working with kinematics, you will be very similar with such, you would already have a good understanding of such graphs, right, where the acceleration is constant, and you would be able to find the gradient, and you would know that the displacement, in other words the distance under that line, would be all of this shaded here, right? And it would be just as simple as this graph on the left to find the distance traveled at 2 hours or 4 hours. But this is a distance time graph, and so you can see, as we found in this graph on the left, that at 4 hours we traveled 200 miles, and that should be, I could maybe clarify that the distance is indeed in miles. And in any case, we would know in this example that if we wanted to find the gradient, right, we could say, well, m is going to equal 200 over 4, which is 50, and that's exactly what we found here, right? The gradient would be our velocity and our speed, and the value would correlate with what we have here on the left graph. Now, the main purpose of just thinking about these is just to, I suppose, maybe a bit of a refresh, just to remind ourselves of some basic things that we know about working with line graphs. But what if we now have, and this is, I suppose, the question that one will ask, and perhaps before one is even formally introduced to calculus, you will have already read, I don't know, math books on maths, or Wikipedia pages, or a book by Roger Penrose, or I don't know, something that already introduces basic concepts of calculus. And so the question is, what if we have, I suppose, the question is, what if we have some line, or curve, I should say, like, I don't know, let's just draw something really arbitrary like that, and we'll just say that this is y equals f of x, right? And what if we have a curve just like this, some arbitrary curve? What do we do now? Knowing everything that we know, similar to the videos on differentiation, how we sort of build up the logic, knowing everything we know about working with line graphs and analyzing line graphs, what do we make of a curve? And really, that's, in some sense, historically, that's what from these types of really basic questions helped inspire the discovery of calculus. But so let's just say, for the sake of exercise, that we drop an altitude down, say right here, like this, right away down. Okay, and let's just say that, we'll mark this point first. We'll call that x, right? This is the x-axis. This is the y-axis. We'll just keep it very simple. Just make everything in this video very simple. And so we'll mark this point as x, and we'll say, okay, the area in this segment, to set everything up, let's just say that the area in this line, we could highlight it in magenta for now, right here, right? This is a of x, let's just say. Use a capital A of x. And we'll say, okay, that's fine. But what if we drop another altitude? Let's just pick an arbitrary point, say right here. And we drop an altitude down, like something like this. What is this point going to be along the x-axis? Well, if this is x, we could say, really very generally, that this is x. This is x plus delta x, right? This is just x plus a change in x, if we want. And then let's ask ourselves, well, okay, if that's the case, what is this point up here? Well, this point is just going to be f of x, right here, like so, right there. And then if we were to ask ourselves, okay, that's all fine, but what is now this area, this entire area, maybe I'll use another color just to sort of highlight that point, light blue or something like this. This entire area, what is this entire area now, up to x plus delta x? Well, we could say very generally that this entire area is just the area A of x plus delta x. Let's just write that in. Let's erase this to avoid confusion now. Actually, I'll just scratch that out, and let's write it like this: x plus delta. Oops. Sometimes my pen tool lags a little bit. X plus delta x. Okay, something like that. And we'll say, okay, that's fine. That's so x plus or a of x plus delta x is this entire area right here. So where does that get us? Well, let's just write it out a little bit. Let's just reflect on it. A of x is area. I'll just write is area from not to x. But then we have a of x plus delta x is the area, so I'll just write is area under curve. I should have probably put under curve at the top here. Is area under curve, let's just say that area under curve from naught to x plus delta x. And if this is true, we could also say, well, the area is, or we could also write it actually in another way. We could just write that it's delta x times f of x, couldn't we? Right? Or so we could say, it is delta x times f of x, which really just means that we have delta x f of x. Okay? So I suppose in that sense what this leads up to, and this is really when I was first sort of teaching myself this, you have to remember this is quite early in one's mathematical career really. I had to get a little bit of a pointer, and so essentially if we set all of this up, what happens when we have very, very, very small values of delta x? Delta x times f of x is this area, right? This entire area. What happens if we get really, really, really small values of a change in x? Well, let's just write it out. What happens for small areas, for small values, for small values of delta x, we get this result: a of x plus delta x is approximately a of x, right? Original a of x, so area, plus delta x times f of x, which we've got right here. So it'd be delta x f of x. And now what we want to do is we know that y equals f of x, right? That's our function. We want f of x to be the subject here. And if one's not sure where all these values come from, again, we've already sort of laid them out, right? A of x is the area from 0 to x. We know that a of x plus delta x is the area of this entire thing. So we can say, following just very simple logic, then the area, in other words, if we read this part right here, right, the area of this entire under the curve up to x plus delta x is approximately a of x plus delta x times f of x. And so we want f of x to be the subject, and now we just need to rely on a little bit of algebra, and this is where it gets really cool. So let's just subtract a of x from both sides, and what do we end up getting? Well, if I spare me from writing all of this out again, if I just copy and paste, we get this here. We get our a x plus delta x minus a of x, right? So we've just subtracted a of x from both sides, so approximately. And then we've got our delta x, f of x, like so. And because we want f of x to be the subject, of course, we're just going now to divide by delta x, both sides, right? And so what we end up with is a very, very cool result. And that is f of x equals, if I again just copy this very quickly, paste it, and we've got our delta x. It's going to be, so we end, the very, very, very cool result is that we get f of x equals all of this here, a of x plus delta x minus a of x over delta x. Now, if one has already been introduced to calculus, they will immediately recognize this as being very, very similar to results that they've probably already been taught. And it's an amazingly cool result. But what follows from this, really, and this is just, again, intuitive reasoning, this isn't so much a rigorous formal proof, but we can say that it follows, and so I suppose, well, let's just say it this way: as delta x, right, as delta x tends to 0, we can say it follows, or it implies, that a prime of x equals f of x. And this is just the fundamental theorem of calculus at this point. That's exactly what this logic is referring to. That is, delta x gets increasingly, it tends to 0. That a prime of x equals f of x, or let's just write it out that we could say that the derivative of a of x, the area, remember, over or with respect to x, equals f of x, and that's what we found. That's exactly what we're basically working toward. That's results. So thus we can say that a of x if equals the integral of f of x with respect to x. And this is, I don't know, when I first sort of learned this, I suppose, and discovered this, I thought it was just absolutely magic. Not literally, I suppose, but just absolutely incredible. And it's a nice intuitive. It's not. I wouldn't call it a proof. It's a nice bit of intuitive reasoning, at least, that explores, or maybe let's say describes, the integral as the area under a curve.